So what I have over here is a stunt motorcyclist, and the motorcyclist takes off of a ramp which is at an angle of theta, and the motorcyclist is going to take off from this ramp right here, and then she's going to land at another platform, and and the distance between these two platforms is given by the variable x. So she's going to clear a ditch or clear a space with a width of x. And then she's going to land on another platform. And she's going to land on this platform right here. But this platform that she wants to land on is a height h higher than her original platform that she took off of. So the original platform was actually shorter than the platform that she wants to land on. So the platform circled in red is higher than the platform that she took off of. And so what I want to do is I want to find what is the minimum velocity, or what is the minimum speed that she has to take off, that the motorcyclist has to take off of, or what is the minimum speed that the motorcyclist has to have in order to clear this ditch with a width or with a space of x. And not only does she have to clear the ditch, but she also has to land on the platform, which is a distance or a vertical distance h higher than her original platform. So we want to find an expression for the minimum speed that the motorcyclist has to take off of in order to successfully make this jump. And let's call that minimum speed v subscript min for minimum speed. In order to successfully make this jump, she has to both clear this ditch and she has to land on a platform which is a distance h higher than the original platform. And so let's start out by creating a coordinate system. And so, and by coordinate system, it's just a coordinate system with a x-axis and a y-axis. So let's arbitrarily choose the origin of our x-axis to be right at this circled dot right here. And this is the origin of our plane, or this is the origin of our coordinate axis. And that origin is at the point right at which the motorcyclist leaves her original platform. So the vertical line I just drew is the y-axis and the horizontal line is the x-axis. And the origin represents the point at which the motorcyclist takes off of. And so let me redraw this coordinate axis down here. And so this is our origin, which corresponds to the same origin on the diagram above. And when the motorcyclist takes off from her initial ramp, she's going to make this parabolic path that's shown in red. And on our other diagram above, the path looks like this, a parabolic path, as she goes from the first ramp to the second ramp. So on our coordinate axis below, it looks like this. The points of the origin are 0, 0. because that's where we define the origin to be, right at the point where she leaves the initial platform. And she noticed that she wants to land on the platform that is a vertical distance h above her initial platform. And so that means that the y component, or the y value that she wants to land on, has a value of h, because the platform that she wants to land on is a vertical distance h higher than her initial platform. That's why the y-axis, that's why I just marked the y-axis right there as h, for a vertical distance h higher than the origin. And so this point right here that's shown in red, or the red dot, that's the point at which the motorcyclist lands on the other platform, or on the elevated platform. So once the motorcyclist clears the ditch, she's going to land at this point right here that's shown on the diagram. And that platform is a vertical distance h higher than her original platform. So what would be the coordinate of this dot right here? So the coordinate of this dot is just the x coordinate, and the x coordinate is just x because the the horizontal distance between the origin and the x coordinate of the platform that she wants to land on, the distance between those two is x. That's the width, or that's the value of the ditch, or that's the space between the two platforms in terms of the x direction. So the x coordinate of the dot, or at the point that she wants to land on, is just this variable x, because that's the distance from the origin to the x coordinate of the platform that she wants to land on. Now, what about the y variable, or what about the y coordinate? So what is the vertical distance between the origin and the point that she wants to land on? So the platform that's elevated, or the platform that she wants to land on, is a vertical distance h higher than the origin. The origin is at the y coordinate of the origin is 0, but the elevated platform is a distance h higher than the origin. So the y coordinate is just h. So now we need to let's come up with the kinematic equation that takes into account the initial x coordinate of, or the initial y coordinate of, the motorcyclist's position, which is 0, the origin, and the final y coordinate of the motorcyclist's position, which is h. So if we come up with the kinematic equation, it's that the final y coordinate, which is denoted with the y, is equal to the initial y component, which is denoted with a y subscript 0, plus the y component, the initial y component of the velocity, which is denoted with v subscript y0, times the time. Now the time is just how far it took, or the variable t stands for time, and that time is just how long was the motorcyclist in the air as she traveled from the origin all the way to the other platform. So how long was the motorcyclist airborne, or what was her time of flight? And we add that to 1/2 times the acceleration due to gravity. But notice here that gravity points downward. So we would have to take that into account since downward is negative. So we would put negative acceleration, -1 times the acceleration due to gravity, or a negative g. So downward is we defined as negative. Upwards we define as positive. Downward we define as negative. So since gravity points downward, we would say that gravity has a negative sign. And multiply by t squared, and t is just how long the motorcyclist was airborne. So let's substitute in values for our y and other variables in this kinematic equation that we just wrote up here. Let's plug in our values for that. And we can get those values from our coordinate axes that we drew right here. So the final y coordinate, or this coordinate right here, would be the final y coordinate. And the final y coordinate is just what is the final y position of the motorcyclist. And the motorcyclist's final y position is just h, because that's the vertical distance, or that's the final y position of the motorcyclist, because she starts out at the origin, but she lands at a y coordinate that's a distance h higher than the y coordinate. So the final y coordinate is just h, and that's equal to the initial y coordinate. But the initial y coordinate, remember, we defined as 0, and that's equal to the initial y component of the velocity. And the initial y component of the velocity is just the initial velocity times the sine of the angle. And that angle is from the angle of the incline right here. And so the initial, or v naught, times the sine of theta is equal to the initial velocity of the y component in the x direction. Or I mean in the y direction, not the x direction. The initial velocity in the y direction. And that's multiplied by the time of flight minus 1/2 times the acceleration due to gravity times t squared. And so in this expression right here, notice that we have a v naught, or a v subscript 0, which indicates the initial velocity. Now this initial velocity is just equal to the minimum velocity, or the minimum speed, to make the jump successful. And so this is the variable that we want to solve for. We want to solve for the minimum speed, which is equal to the minimum, or which is equal to the initial velocity, or speed, or the v subscript 0. So we just want to solve for the v naught. And so notice that we know what the variable h is. It's indicated on our diagram. It's a given variable, and we want to solve for the v naught, or the initial velocity, and we know the value of sine of theta, but we don't know what the t is. We don't know how long the motorcyclist is in the air. So we would have to come up with a different expression for the value of t in terms of our other given variables. So let's come up with a different expression for the variable t, because we don't want to solve for how long the motorcyclist was in the air, but instead let's substitute a different expression in for t rather than just solving for what t is. So let's consider, then notice here that this kinematic equation is in the y direction, but let's consider a kinematic equation in the x direction. So the final y, so we one of our kinematic equations that's similar to this kinematic equation right here, but in the x direction, is that the final x coordinate of the motorcyclist is equal to the initial x coordinate of the motorcyclist, which is x subscript 0, plus the initial component of the velocity in the x direction multiplied by the time of flight plus 1/2 times the acceleration in the x direction times t squared. But we can simplify this equation down further, because as the motorcyclist makes the jump, the acceleration, the velocity in the x direction stays constant, or the x component of the velocity right here is constant. So if the x component of the velocity is constant, that means that the acceleration in the x direction has to be 0, because the x component of the velocity stays constant. So that means that the acceleration in the x direction equals 0, since the x component of the velocity remains the same throughout the flight, or throughout the motorcyclist flight. So the acceleration in the x direction equals 0, so we can just erase this entire term, since that entire term becomes 0. So let's solve for t in this equation. So our final x coordinate is just equal to this x coordinate right here, which is just the width, or the how far apart the two platforms are from each other, which is drawn on our diagram. So let's simplify this expression. So the final x coordinate is equal to the initial x coordinate, which is just, and the initial x coordinate is just the origin, which is 0, plus the initial x coordinate of the velocity in the x direction times the cosine of theta. And we take the cosine of theta because since we want to find the velocity in the x direction, we would just multiply the initial velocity by the cosine of theta in order to get the x component of the velocity. Now let's just solve for t. solving for t, or the time of flight, we get the following expression. So now, since we have an alternative expression for t, or the time, in terms of our given variables. Now let's just substitute in this equation into our earlier equation. So the time of flight is given by this expression, and let's just substitute in this entire expression in for this value of t right here, and also for this value of t squared. And then let's solve for our minimum speed. So now if we substitute in this value of t, or this alternative expression for t, we just get the following expression. And then minus 1/2 times the acceleration due to gravity times t squared. And so we would just have to square this entire expression of t. So if we distribute the square to each of the variables in t squared, we get the following. And so notice that we can simplify this expression down a little bit, because there's a v naught in the numerator and the denominator. And so v naught divided by v naught, we could just divide those out and those would cancel out. And so notice that we're solving for v naught squared, or we're solving for this variable right here. So let's isolate for that variable. So notice that sine of theta divided by cosine of theta, that would just give us tangent of theta, and tangent of theta multiplied by x. So let's just bring that entire term over to the left side, or let's subtract that term and bring it to the left side. We would get this, because sine of theta divided by cosine of theta is equal to tangent of theta, and that's multiplied by x. And notice that since we're solving for v naught squared, let's get rid of this negative sign right here. If we multiply both sides by a negative 1, we would have to that would get rid of the negative on this side, but we would have to multiply a negative on the left side. So we would just put on a negative sign into this expression right here. So there's a negative sign that would go on there, and this negative sign would, or this minus sign would turn into a positive, since we're multiplying both sides by a negative 1. And so this side would become positive times g squared, and so now let's solve for v naught, or the minimum speed. Let's multiply both sides by 2, and then let's divide both sides by g. So if we multiply the left side by 2, we would get this. And I'm just going to rearrange this variable so that this term becomes first. The x tangent theta becomes first. So, and all of that is divided by g. And now all of that equals x squared, and the same as before. So now we're solving for v naught squared. So let's isolate the v naught. We can do that by just multiplying both sides by v naught squared, and then that would bring the v naught squared into this side over here. into the left side, and then we can isolate the v naught squared from there on. If we multiply both sides by v naught squared, we would get the following expression. So if we multiply the right side, if we multiply the right side by v naught squared, we get rid of the v naught squared from this right-hand side expression. And that will be multiplied by all of this. And that would be equal to cosine of squared theta. And so now let's isolate the value of v naught squared. In order to isolate the initial velocity squared, we would have to multiply both sides by g, and then let's divide both sides by 2 parentheses x tangent theta minus h. And that way we can isolate v naught squared. Multiplying both sides by g, we get this, and dividing both sides by 2 parentheses x tangent theta, we would get this expression. And then notice how in order to finally isolate the v naught squared, we would have to get rid of the square on the v naught. And in order to do that, we would have to take the square root of both sides. If we take the square root of both sides, we can finally get rid of the square on the v naught. And so notice that we can simplify this down even further, because the x squared value and the cosine of squared of theta, those both are perfect squares. So we can just, the square root of both of those variables, we can just take out of the square root, because the square root of a perfect square is just the variable itself. We would just get rid of the square root, and we would get this following expression right here. So this is the simplified formula right here, meaning this entire expression right here is the minimum speed that the motorcyclist would have to travel at in order to successfully clear the ditch and also land on the platform that's a vertical distance h higher than the initial platform.